Volumes of revolutions, the last topic in Core 3. We've got 2 lessons covered in this presentation. First one is volumes where shapes rotated around the x-axis, and the second lesson, slightly less straightforward, when we rotate around the y-axis. So what do we mean by that? Well, we'll have a look at an area first. If we look at the area between y equals x, the line x equals 1, and the x-axis, you can see we've got this triangle here. If we rotate around the x-axis, what shape do you think we get? So rotating like that around the x-axis. And the answer is we get a cone lying on its side. If we think about the volume of that cone, well, there is a formula for the volume of a cone. It's this here. And if we plug in our values, we've got 1 for r and 1 for h. So we just get a third pi as the volume. So for a nice straightforward shape like a cone, we could use methods like that. That's not always possible, however, and here we see we've got a very odd shape. The volume is pi times the integral of y squared between the two limits, a and b. So where we've got our f of x, our y equals a function of x, is the equation of the curve. And a and b are the x-coordinates of the left and right edges of the area, the limits for the integral. And generally speaking, we'll leave answers in terms of pi, so they'll be exact answers. We substitute for the y the function of x, so we'd square the function of x. So here, because y equals x, y squared equals x squared, we would integrate this, we get x cubed over 3. We evaluate by placing in the 1 and the 0, and we get a third pi as our answer. Notice we only bring the pi into it right at the end. So a nice easy one there. We started off with y equals x, and we see we get the same answer as we got using the formula. We'll have a little look at why this works. If we think of narrow strips like this, we've got lots and lots of tiny pieces that are approximately cylinders, like pennies on their side, each with a volume like this. The r is the y value. We're adding an infinite number of these elements. So in other words, it's like a sum of this, which is what an integral is, isn't it? So between a and b, we're doing that. We're summing, if you like, the integral of pi y squared, but pi being a constant, we can take it out of the integral. So we get an infinite number of little cylindrical slices. So we can use this area of a circle formula times the width to find out the volume. Okay, let's have a look at some examples. First one, we're looking at the area formed by the curve y equals x times 1 minus x, the x-axis from x is 0 to x is 1. And we're rotating 2 pi radians, in other words 360 degrees, to find the volume of the solid formed. For the second one, we've got an exponential. We've got y equals e to the x, and we're looking at the x-axis of the lines x equals 0 and x equals 2. And again, rotated round the x-axis a full turn. Don't necessarily need a sketch, but as we're just starting with this, it will help us to understand what's going on. So for the first one, this is what it looks like. It's a quadratic, isn't it? You can see that if you multiply out, you get x minus x squared. It's a minus x squared one, so that's why the parabola is this shape. So that's what it looks like. That's the area. If we rotate around the x-axis, hopefully you've got an idea what the shape's going to look like. Right, be very careful about your y squared. Make sure you get it right. To find y squared, we need to square this out, don't we? Don't forget, if you've got a product and you square it, you need to square both factors. And the easiest way, really, because it's only squared, is to multiply out, and then we can integrate term by term. Okay, so that's the y squared. We'll use that now. If we integrate, we get x cubed over 3 minus 2x to the 4 over 4 plus x to the 5 over 5. We can cancel there, can't we? So we just get half x to the 4. And then if we stick our 1 and our 0s in, well, all of the x terms, because there's x in the numerator, will be 0. So we just get this bit here, and we end up with pi over 30. For the second one, very familiar y equals e to the x curve. Hopefully you can envisage this shape if we rotate it. It's going to look a bit like a loud hailer, isn't it? Okay, if we square e to the x, we get e to the 2x. So that's the integral we're looking at. So stick the 2 in, that's what we get. E to the 0 is 1, so we just get minus a half here, don't we? And we end up with pi times e to the 4 minus 1 over 2. Okay, your turn. Have a go at these. If you're successful, then you're ready for the first lesson. So pause the presentation, have a go. Okay, I'll show you the answers. So you should have got the integral. It's 1 over x all squared. Remember, if you're squaring a fraction, you square the numerator and square the denominator. And for our y squared, we end up with 1 over x squared. We take that up and call it x to the minus 2. And then if we integrate, raise the power by 1, divide by the new power. And then once we've got that, we get minus 1 over x. We can plug in our two limits. So the 2 first, and then the 1. So we end up getting minus a half plus 1, which gives us a v value of pi over 2. And then for the second one, don't forget for your y squared, what you need to do, you need to square both of these, so you end up with x squared times x, which gives you x cubed, doesn't it? Integrate to x to the 4 over 4, and if you put in your 2 and your 0, well, obviously the second one, x to the 4, when we've got 0 is just 0. So we've just got 2 to the power of 4 over 4, which is actually 2 to the power of 2, isn't it? Because it's 2 to the power of 4 over 2 to the power of 2. So it's 4 pi. Okay, so for the second lesson, we're looking at rotating about the y-axis. We use a very similar formula, we just swap x and y. So it becomes, for the volume, pi times the integral of x squared with respect to y, where x will be a function of y. So we need to rearrange if we start off with y as a function of x. Note the different limits. If we're given limits that are to do with x, we would need to find the equivalent limits to do with y. Okay, so we're integrating with respect to y. So we're looking at this area here. We already have y limits, so we don't need to worry about the limits. We can put them in as 0 and 2, but we do need to rearrange this equation here. So if y equals root x, x will equal y squared, which means x squared will be y to the power of 4. So our integral becomes pi times y to the power of 4 with respect to y, and between 0 and 2. So same process now, raise the power 1, divide by the new power, plug in the limits, we get 2 to the power of 5 over 5 minus 0, and we get 32 pi over 5. Okay, have a go at these. Okay, here's the answers. That's the area we were looking at. We've got y equals x squared. So x squared just equals y, doesn't it? So that's a straightforward putting it in there. We get y squared over 2 when we integrate, and if we put in our limits, we get 9 pi over 2. For the second part, part B, y equals 1 over x is what we start with. That means x equals 1 over y, so x squared will be 1 over y squared. If we integrate 1 over y squared, it goes to y to the minus 1 over minus 1, so it becomes minus 1 over y. Plug in the limits and we get pi over 2.